Now let's do a little proof. Show you how we can easily prove things. Our theorem that we're going to try to prove is that consecutive interior angles are supplementary angles. We have enough information to prove this theorem. Now, what we're going to be trying to prove is that the measure of angle 3 plus the measure of angle 5 is 180 degrees, and that the angle measure of 4, or the measure of angle 4, plus the angle measure, or the measure of angle 6, is also 180 degrees. Consecutive interior angles. Well, our consecutive interior angles are 4, 6, 3, 5, and we want to prove that they're supplementary, meaning that they sum to 180 degrees. Well, from the definition of corresponding angles, we know that the measure of angle 1 is equal to the measure of angle 5, and the measure of angle 3 is equal to the angle of measure 7. That's a definition of corresponding angles. Angle pair 1 and 5 are congruent, have the same measure, and so do 3 and 7, have the same angular measure. Now, that being the case, if we sum angle 7 with angle 1, that will be the same as adding to angle 7 angle 5, because 1 and 5 have the same measure. So measure of 7 plus the measure of angle 1 will be the same as the measure of angle 7 plus the measure of angle 5, because angle 1 and angle 5 have the same measure. Now, by we're doing this by substituting. What we're doing is if we take angle 7 and add to it angle 1, then we can substitute angle 5 in. This is substitution. And we get this relationship. Now, we know that angle 5 and 7 are supplementary angles. 5 and 7 sum to 180 degrees. Looking at it right here. So, angle 5 plus angle 7 is 180 degrees, so therefore 7 and 1 also must sum to 180 degrees. Now, also 1 and 3 are supplementary angles. If you look at it, if I add 1 to 3, I get this angle, which is a straight angle. So 1 and 3 are supplementary angles, and so are 5 and 7, which we just established. So we can say that if we add to angle 1 angle 3, the sum of angle 1 and angle 3 is 180 degrees because they're supplementary angles by definition. Now we also know that angle 5 and angle 7 are also supplementary angles. They sum to 180 degrees. Now, let's add these two equations together. So I've got angle 1 plus angle 3, and I'm going to add to it the left side here, which is angle 5 plus angle 7, and that is equal to twice 180 degrees. I can add two equations in this fashion. This is a basic algebra maneuver. I can equate the left side of two equations and set it equal to the sum of the right sides of the equation. Now, we'll use a property called associative property, which tells us for any numbers we can rearrange the order in the sum. So I'm going to rearrange it in this fashion. I am going to associate angle 3 to angle 5 and angle 1 to angle 7. So I'm just going to mix the sum around. So I've got angle 3 plus angle 5 plus angle 1 and angle 7. All I've done is rearrange this, and this is equal to twice 180. That is, with angle 3, I put angle 5, and with angle 1, I put angle 7. This is called the associative property. I can rearrange the terms in a sum. Well, we've already established that the sum of angle 1 and angle 7 is 180 degrees. Angle 7 plus angle 1 is 180. So this is 180. And we have twice 180 on that side, so we can move that out or cancel one of the 180s on the right hand side, and we have angle 3 plus angle 5 then is equal to 180 degrees. So we've just proven that angle 3 and angle 5 are supplementary angles. That's the definition of supplementary angles. Now, in like manner, we can prove that 4 and 6 are also supplementary angles. And I'll do that by using what we just already proved. Okay, by definition of supplementary angles, we know that angle 3 plus angle 4 is equal to 180 degrees. 3 plus 4 is this plus this, which is a straight angle. So 3 plus 4 is 180 degrees by definition of supplementary angles. And angle 4, or angle 5 plus angle 6, is also supplementary angles. If we look at 5 and 6, that's this angle here, which is another straight angle, so that's 180 degrees. Now let's add the two equations. So we have angle 3 plus angle 4 plus angle 5 plus angle 6 is equal to twice 180. Again, by associative property, I can group these any way I want. So with angle 3, I'm going to put angle 5. So I have angle 3 plus angle 5, and what's left over is angle 4 paired with angle 6. And that's twice 180. Well, we just proved that angle 3 plus angle 5 is 180 degrees, so we can subtract that off here, and we end up with angle 4 plus angle 6 is equal to twice 180 minus 180, or just 180. So the sum of angle 4 and angle 6 is 180 degrees. That's a definition of supplementary angles. So angle 4 and angle 6 is 180 degrees. All right, now let's prove another theorem. We're going to prove that alternate angles are equal. That is, that we have alternate interior and alternate exterior angles. So the alternate interior are 3 and 6, 4 and 5. Alternate exterior are 1, 8, 2, and 7. So what we're contending here is that angle 3 is equal in measure to angle 6. Angle 4 is in equal measure to angle 5. Angle 2 is equal in measure to angle 7. And angle 1 is equal in measure to angle 8. These are our alternate angles. Both interior and exterior alternate angles are equal in measure. That's what we want to prove. Well, we just proved that angle 3 and angle 5 are supplementary angles. They sum to 180 degrees. That was just proven. Now, by definition of supplementary angles, we know that 5 plus 6 is 180 degrees because it gives us a straight angle, 5 plus 6. So we know that angle 6 plus angle 5 sums to 180 degrees. Now, by the definition of corresponding angles, we know that angles 2 and 6, 1 and 5, 4 and 8, 3 and 7 have the same measure. That's what the definition of corresponding angles is. Well, we can take these two equations like we did before. We can add the left sides and the right side. So we get angle 3 plus angle 5 plus angle 6 plus angle 5 is equal to twice 180 degrees. Or another way we could write this, rather than doing it that way, we can also write it in a different form. We could, since these two sums are equal to 180 degrees, we can sum the angle. Equate the two angles, sums. 3 plus 5 is equal to 180, which equals to angle 6 plus angle 5. Well, angle 5 appears on both sides. We can cancel out, so we end up with angle 3 is equal to angle 6. Okay? We just proved that one. Now, by definition of supplementary angles, 1 and 2, the sum is 180, and also 6 and 8. If we look at this sum, this is angle 6, this is angle 8, they sum to 180 degrees. So we can write down that the sum of angle 1 plus angle 2 is 180 degrees, and the sum of angle 6 plus the sum of angle, or the sum of angle 6, the measure of angle 6 plus the measure of angle 8 is also 180 degrees. Now we can equate these two again, like we did. The measure of angle 1 plus the measure of angle 2 is 180, which is also the measure of 6 plus the measure of angle 8. Now, with the definition of corresponding angles, we know that the measure of angle 2 and the measure of angle 6 are the same. So we can cancel those out. Those two measures are exactly the same. So we're left with the measure of angle 1 is equal to the measure of angle 8. So we've proven this one. So in the like manner, you can prove these. I'll let you do that. You can prove these two in similar manners as we did. So we've just proven that particular theorem. Now we'll look at triangles. Undoubtedly, you've heard somewhere along the line that the sum of the interior angles of a triangle sums to 180 degrees. We can now prove that given what we have and what we've developed so far. So we want to prove that the sum of the interior angles of a triangle is 180 degrees. Let's call the three angles on the interior of the triangle A, B, and C. Now what we're going to do is extend out the baseline of the triangle, and we're going to draw a line parallel to it that intersects the vertex of angle B. So this line is parallel to the base. These two lines are parallel. Now what we're going to do is extend this side of the triangle out this way, and this side of the triangle out that way. Now we know by definition of vertical angles, we have this line intersecting with that line, so this is also angle B. Those are two vertical angles, so that is angle B. Now, if we consider two parallel lines and consider this as the transversal to these two parallel lines, we know that this angle and that angle are the same. That those angles are what we call consecutive angles from before. Now, this angle here is angle C by definition. And the same thing here. This angle A will be this angle here. This transversal cutting the two parallel lines make what we're seeing is we have two parallel lines. This is angle A, so this 4 is also angle A. So that's angle A. Well, what's the sum of A, B, and C? Well, angle A plus angle B plus angle C is this angle, which is a straight angle, and we know straight angles sum to 180 degrees. So there's a general proof that the sum of the interior angles of a triangle sum to 180 degrees. Let's look at a convention that's used for establishing the congruency between two triangles. If we have a general triangle, we can designate we have three sides, side, 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 and three interior angles, angle, angle, angle. Now, we can specify three things, either a combination of angles or a combination of sides in establishing congruency. That is, we could specify side, side, side. That is, if we specify the lengths of three sides, we could establish congruency. Or if we have a side, an included angle, if we have side, the included angle, and another side, or if we have an angle, and then a side, and then another angle. So we have angle, side, angle. And another way we could do it is if we have an angle, and a side. And there's two other ways we can go if we specify a side, and an angle. Or if we specify three angles, angle, angle, angle. Well, these four here can establish congruency, but these two cannot. Let's investigate that. If we have one triangle and we specify three angles, and we have another triangle, we could have another triangle with exactly the same angular measure, but different size triangle. So these triangles are not congruent. Remember, congruency means the same size in the same shape. These are the same shape, they're similar, but they're not the same size. So angle, angle, angle does not work for establishing congruency. How about side, side angle? Well, if we're given a side and say another side and this angle, okay, so we've got this side, and this angle. Well, if you look, all we'd have to do is swing this side over. It would have the same length as this side. But this triangle here is not congruent to this triangle, even though they have this side length and this side length specified. We could just swing this side over to get this triangle. So this will not establish congruency either. So those two cannot be used to establish congruency. What about, say, side, side, side? Well, if we have two triangles whose three sides are identically equal in measure, the same lengths of sides, if we call that A, B, and C, and this has A, B, and C, then the two triangles will be congruent. They'll both be the same shape and they will be the same size. How about if we do side, angle, side? Well, side, angle, side, we have side, the included angle and another side. So we could specify side, and then we'll establish an angle, but we mark off on that angle a specific length. So we've got a side length, and an angle. Well, we can complete this other side, and there's no other length that could be. So this can be used for specifying congruency, and you can go through the same arguments for these. For example, angle, angle, side. Let's say I have this angle, and I add to it another angle, and then, see, this angle can go out forever, this angle can go out forever on its length, but if I have this angle, and I specify this side length, I have uniquely determined that triangle. So that's a designation that can be used for establishing congruency that we may use further on down the line. The last topic that I'm going to discuss in this first lesson is a relationship between arc length, angular measure, and radius on a circle. This is a very important relationship that's used in deriving equations of perspective, parallax equations, and used a lot in celestial mechanics as far as how objects appear to the eye. The angular size of these objects appear to the eye. And the way it's derived is, say we're given a circle of radius r. We have a center of the circle and a radius that goes out to the perimeter on the circle. Now we have a section of arc on the circle, and we will call the measure or the length of that arc S. That's arc length. So S denotes arc length, and theta is the angle that subtends this arc length. Okay, that is, if we take the length of arc S and take the endpoints and then draw a line from the center of the circle to the endpoints of that arc, we say that this arc is subtended by this angle theta. Now, what we use is the fact that in the circumference of the circle, if we go one full revolution around the circle, that angular measure all the way around is 2 pi radians. And the arc length will be the perimeter or the circumference of the circle, the total perimeter around the circle or its circumference. And we know that the circumference on a circle is 2 pi radians times the radius. Now, the relationship is that if the arc length S is just a portion of the circle, we can set up a ratio that S is to the circumference as the angle that subtends S, which is theta, is to the total angular measure around in radians, or 2 pi. But we know the circumference is 2 pi r, so we can substitute in here S is over 2 pi r as theta is to 2 pi. Well, we have 2 pi on each side. We can cancel those out. So we're left with that theta is equal to S over r, or the arc length S is just the angular measure in radians times the radius. Very important relationship, that if you have a side of an angle of length r and you sweep it through an angle theta in radians, then the amount of arc, the length of that arc swept out, S, is just the angle. I'll put a small RAD to say that the angle has to be in radians. You cannot use degrees. It has to be radians. So if you have an angular measure in degrees, you have to convert it to radians to get the proper relationship. So S is in length, R is in length, radians times the radial distance out gives you the amount of arc swept out. Now, let's see how this works. Suppose we sweep out an angle theta. Here is our angle theta. Now, if we go out a radius, say R1, we will sweep out this amount of arc. This side and this side are the same length. That is, we're sweeping out this radius R1. So this is S1. So the relationship here is that S1 is equal to theta times R1. Now, if we go out further, say a radius R2, where this length here is R2, and we sweep out through the same angle, we're going to sweep out a larger arc. Call this S2. And then this side length here is R2. So what we have is theta, this length is R2, this is R2, and this is S2. And the relationship here is that S2 equals theta R2. We're sweeping the same angle. So what we have here is a perspective type thing, is the further you go out, as you sweep an angle theta in radians, you sweep out a larger arc. The further out you go. I mean, it makes sense, right? Now, if we have S1 equals theta R1, and we have S2 is equal to theta R2, and we ratio these, then the amount of arc, the ratio of the arcs are equal to the ratio of the radial distances out. So this arc length is proportional to the radius that sweeps it out, as this arc is proportional to this radius. So the ratio of R1 to R2 is the same as S1 to S2. That's what we have here. A very important relationship to keep in